Okay, good. So we're gonna start with this result that we got last time. So deducing the central force from the orbit. That's what we did last time. I'll set this up again. So, and this will get us Newton's law of gravity fair and square. So deducing central force law from the orbit. So from the equation of the orbit. And I'll just remind us what happened there. So you have, say, as the perfect example, you've got the Kepler ellipse, and we had R equals P 1 plus E cos phi, and the parameter of the eccentricity we defined. Right, so we have the orbit, and this came from using plane polar coordinates. So we have m r second derivative. So this is a central force in general, and when you have plane polar coordinates, you have m r second derivative minus r e dot squared equals f of r, and you have m 2 r dot e dot plus r phi double dot. There's supposed to be two dots. Try it again. R phi double dot equals what on the central force? 0, exactly. So that was the plane polar coordinates. And the second equation gives you m r squared phi dot equals L, which is a constant. And you can take that into the first equation here, and then we have r dot, which is dr dt, which is dr d phi dt. Okay, so those are the ingredients allowing us to turn this simply into an equation involving phi and dr d phi. So the upshot of that calculation we did last time, which I'll write down, is this right here. So when you plug those things in, this is the last thing we pretty much had. Your force law looks like this. L squared over m r to the fourth d squared or d squared minus 2 divided by r dr d phi quantity squared minus r. So, okay. So that can involve a little bit of work, but this is going to be an interesting problem. And as I said, the homework was to take this the orbit law that we found. By the way, that's not just the ellipses, those include the hyperbolas and parabolas as well. So you take that into f of r here above to obtain f of r. When you resolve everything, you're going to get the minus sign as well, minus alpha over r squared. We have u of r equals minus alpha over r. But before well, you guys are going to do that, okay, and that's pretty satisfying. But what we also want to do is just some basic examples and see what this thing delivers, okay? So we actually want to apply it. I'll put a note here though. Your 1 over r squared that you're going to obtain is going to be 1 plus e cos phi P, quantity squared, right? So when you do all these operations and you're working away and you finally end up with this, then you know you've succeeded, right? That's what because the 1 over R is 1 plus E equals V over P. So just to kind of see what you're shooting for. Because on the way there, you're getting quite a bit of that kind of stuff. Yeah, you have to resolve that. But let's do an example to kind of see this formula in action. Suppose we just have R of phi is equal to some constant times phi squared. What kind of a trajectory is that? What kind of an orbit? What does that orbit look like? Before we go into there, we'll find out what its force law is. And we can make these up all day at this point. What do you guys think? What does this orbit look like?
Hyperbola?
Not a hyperbola. And I'll just make sure for the record, C is just some constant. So remember, we're measuring phi, out at some point here, there's your angle phi. Not a parabola. Anybody? So you see R is changing with phi, and it's growing, right? It's growing quadratically with phi, but since that R is just the distance from the origin, from the center, from the origin, the center of potential, it's some kind of spiral, right? So you've got something that's growing like that, right? And so that would be a legitimate object. You can imagine, well, something can spiral in and collide with the center of attraction. Okay, so let's go ahead and do this here. We just have to do dr d phi is equal to 2 times c times phi d squared r d phi squared is equal to 2 times c. And now we'll just go ahead and plug that in here and see what happens. So then our force law, we've got L squared over mr to the 4th. D squared r d phi squared, we have 2 times c. Minus 2 over r. And then dr d phi squared is 2c times phi squared. Or we'll do it in 2 steps, no problem. Because we got to recover the expression for r, that's okay. So 2 over r, 2 times c times phi, quantity squared minus r. So what we have to do is we just have to simplify that and express phi squared in terms of r. But phi squared is r over c, right? So we'll have equals L squared. L squared m r to the 4th, 2c minus 2 over r. We've got 4 c, and then we've got a c phi squared left over, right? And that would be r times r minus r. So we have L squared, bring this up to here now. So we have here f of r equals L squared m r to the 4th, 2c minus 8c, so negative 6c minus r. So to finish this up, look at our force law. We'll keep these minus signs out front. So we have minus 6 C L squared over M r to the 4th, and then minus L squared over M r cubed. If you have anything else to say about that? Yeah. So the minus signs show that that's an attractive force, okay? So it's an attractive force, we've got the minus signs. It's higher than r squared, it's, r cubed and r to the 4th, okay? And so what we've learned here, we kind of got this for free without doing anything difficult, is that force laws with this high of a power will have in-spiraling solutions. And like I said, you can make these up all day. Okay? You just make up some kind of RFE, plug it in there and see what comes out. So I'll just put here attractive because of the minus signs. And the 1 over r to the cube. So if you ever wondered what an r cubed or r to the 4th law would do, now you know. Get spiraling in. We couldn't have plugged that, or couldn't have plugged that into our integral that we did the other day. Right? So this is a good way to get at some stuff. But of course, you guys are after bigger fish. Namely, we want to plug this in to improve students' law of gravity. Yeah. Good. So there are a bunch of interesting topics in central force, but I kind of want to move on.
I have a question.
Yeah.
So I was trying to make a simulation of like two-body problem, and then yeah, I covered the problem when like particle approaches the origin, right? The force becomes infinite.
Yeah.
How do we resolve that?
Numerically,
Yeah.
don't let it get too close.
Oh, it's this.
Probably, yeah. Because those are point particles. Yeah, if you were to make finite sized particles, then you could end up with collision as well. But it's definitely possible.
If I have like a hollow sphere, right? Would the force inside the sphere be 0?
No, would not. It's a uniform sphere, it's a hollow shell. Actually, that's a good question. The thing is this, so if you have a central force problem and you're mathematically accurate, as long as you give it some angular momentum, it shouldn't come arbitrarily close to the center. Those could be numerical errors. So you have to make sure it has some, what do we call it here, angular momentum. Okay. So in the system of just a point particle and a point center of attraction, any angular momentum at all should keep it from falling in. And if you build in, just for fun, a stronger, greater power than 1 over r squared, you'll see them spiral in. That might even be interesting to do as well. Okay. You could just build in just for starters, 1 over r cubed law. And then you should see things spiral, and that would be a nice test. Those kind of simulators are probably available even, but if you make your own, all the better, right? Because I've seen 3-body ones before. We can type in some bodies.
It's like very chaotic.
3-body ones are kind of wild because every now and then a particle, one of the 3 bodies will be ejected from the system, never to return. So that's also possible. Good. So yeah, this will be a great problem because we're going to get Newton's law out, and that's a fantastic deduction actually. The first way we got it when we used Kepler's third law on circular orbits is probably what he did too for the first go around, but then to get it exactly like this is pretty satisfying. Okay. That question came up, how did we have that 1 over r cubed? Remember that 1 over r cubed potential? I'll go ahead and remind ourselves. Because that 1 over r cubed and this one are different. Okay. So how about the absolute angle? So we can return to the absolute angle discussion briefly. And when I hand those back, then we'll even discuss it a little more. Go ahead. Okay, so now we've talked about incoming, in-spiraling potential. So let's recall this absolute angle discussion. You know, we had C was pi over root 3 plus u double prime r naught times r naught divided by u prime of r naught. Okay, we don't need to go anywhere with this. And then that homework problem, we had u equals minus alpha over r squared, I'm sorry, over r. Plus beta over r cubed. And the question was, what's the significance of this 1 over r cubed? Okay. And what I said was, it's a small correction, so it definitely is not holding true as r goes to 0. It's really only for larger r. You guys remember that, right? And Thomas even asked, what kind of a Taylor expansion is that, and so forth. So we're going to get into that now. But for the moment, especially since we just talked about 1 over r cubed being an in-spiraling potential, this is really only for small beta. Okay, but then we were able to say, let's go ahead and call this minus alpha over r times 1 minus beta over alpha r squared. Right? That's just the arithmetic there. Multiply that out, you get that alpha canceling, you got the r cubed. And the thing is, this part has to be much less than 1. So beta over alpha r squared much less than 1. And that entails beta being small, but it also entails r being close to the Kepler orbit radius. Okay. Okay, much less than 1. So this is just a correction term for small beta. So this is a perturbation of sorts. So what we want to do is investigate how that happens, and then we'll develop a formalism for it. Very important, because the real potentials, as soon as you have something that's not perfectly spherically symmetric, as this is not, right? Something that's a little oblate, then you no longer have minus alpha over r. In fact, you get these extra terms naturally. So that's what we're going to start to investigate. And so what we're going to do next is extended mass distributions. So there's a point mass, and for the moment not a spherical, extended mass distributions. And a good one to start with, and we'll get to those bigger ones, but a good one to start with is just to find the potential of a linear mass that goes on the x-axis from minus L over 2 to plus L over 2. And we're going to ask, what is the potential? Here's the x-axis. At some point x. What's the gravitational potential energy at some point x? And the way we'll find u of x equals question mark. So how do we do that? We add up a bunch of point masses along this line. So we're going to do an integration. And what we have is, we can say du is equal to minus alpha. Now we gotta go back. We're going to do v of x. We define a little more terms before we do this. V of x such that u of x is equal to m times v of x. The way you do it with electrical potential, right, we have a charge, here you have a mass. Okay? And the reason for that is we're going to have a mass distribution. So we know that U, say, two masses, U is equal to minus G M over bar. So that puts us on familiar ground. So now we're going to integrate something up here. And we'll have a v of x is minus G M over R, and dB, actually we have the x right now, it's d, so dB of x is now going to be minus G dm over x, and we're going to do an integration. Okay. So we're going to integrate over the total mass distribution, and that will give us the gravitational potential out here at point x. That's the plan. Yeah. Okay. So we have a, let's see, from this point x to some little dm here, we can have this thing at x prime, so we'll have an x minus x prime. So we have v of x is going to be minus g integral dm over x minus x prime. We're going to do minus L over 2 to L over 2. So yeah, every little dm here, and x will be greater than L over 2, so everything will be safe here. So what we're going to have is the dm is going to be lambda dx prime. I could put prime, actually it's a good habit to put the primes on the m there as well, so we see what we're integrating over. And that point x here, right, that's the argument, is that point out here. And if it's a uniform mass distribution, we can just say it's the total mass over L times dx prime, mass per length, okay? So now we're ready to plug in. So we have equals minus g. We've got that lambda there, so gm over L integral dx prime x minus x prime. We're just going to have x positive. I don't have to worry about the absolute values. Minus L over 2 to L over 2. And keep going. Minus gm over L. Now we have a natural log here, but so we have natural log of extra minus sign there because we're integrating with respect to x prime. That turns that into a plus. And now we want to be careful here. So m over L, and we're going to write natural log of a big quotient. So we'll have x minus L over 2, and then x minus negative or x plus L over 2. Now, as is often the case with these reasonably simple things, there's already an expression you can't really just look at and make heads or tails. So we're going to manipulate this thing a bit and turn it into something that we recognize. So without any approximation, I'm going to make the numerator and the denominator dimensionless. I'm going to divide the numerator and denominator by x. So we can actually just continue on here. We've got g m over L natural log of 1 minus L over 2x, 1 plus L over 2x. And at this point, the argument will be dimensionless, and we'll expand out that natural log. Now, I'll go ahead and leave this picture up here. It's not bad. And, continue on here. So we're still working with v of x. We've got gm over L times natural log 1 minus L over 2x minus natural log 1 plus L over 2x. So there's our grand result that we're actually going to be able to analyze. And this is the answer to that question that came up the other day about the small quantity. See, by doing this, we're actually going to expand this in terms of large x. And L over 2x is going to be our small quantity. So principally, you could say if L over 2x is 0, then I'm out at infinity. So that's the nature of these small quantities that we were just talking about also with the beta over r cubed. Right? We're coming at them from a great distance. And we did it by hand here. We're going to get a formalism that helps us do this. Okay, so this is our v of x, and we're out here to the right. We can get the same thing over to the left, no problem. So what we want to do is expand this for small L over 2x. Okay. So I'm just going to actually write this out once more if we have support. So here's our result at the moment. V of x, g m over L, natural log 1 minus L over 2x, minus natural log 1 plus L over 2x. Good, so now we can clear this up. Okay, so we need another letter. So our small quantity, so now we'll just use z equal L over 2x, and that's nice, that's dimensionless, and we'll let that be much less than 1. Okay, what's the series expansion of the natural log? Natural log of 1 plus z right? It starts out just being linear in that small quantity. And in fact, you can do the Taylor series, but the natural log does this, right? When at 1, it goes to 0. This approximation, this Taylor product really is just saying that the slope is equal to 1 at that point. Okay. So yeah, we were able to make short work of this thing. So for, again, L over 2x much less than 1, which means we're at a great, what does that mean? It means we're at a great distance, a distance that's much, much greater than L. Okay. So what we're getting now is V of x, our approximation, Gm over L, negative L over 2x, minus L over 2x. And Gm over L, negative L over x, equals minus Gm over x. So what's the punchline here? Is that this is the potential of a point mass. The potential of a point mass, and for the homework, you guys are going to enjoy showing that the next term in this Taylor expansion, the next non-vanishing term, is going to give you the 1 over x cubed that we found in gravity already. Okay? So this is a really satisfying situation. Okay? Set of events here that important note. This is the potential of a point mass at the origin. So yeah, if you're far enough away from this thing, then here's our minus L over 2. L over 2, we had just a linear mass distribution, so no extension in any other dimension. And if we're far enough away from it, then it behaves like a point. Okay. Looks like a point, behaves like a point. Of course, looking at it on end looks like a point anyway. So I'm going to add, what do we have for homework this week? This is all before the exam anyway. So.
Last check that was assigned was given R of V show f of r is negative alpha over r squared.
Were there many before that?
There were 2 before that.
2 before that. Yeah, we can add this to the mix. We might make these also just be due on Monday. We'll see. Okay, so what we want to do for the homework, and on this type of problem, it's best just to repeat everything I did, because you want to expand this to the next order. So expand natural log 1 plus z to third order, and find v of x, which we already see is going to be approximately minus gm over x, and I'm just going to put a plus a over x cubed, and you'll find out what that letter a is, okay? But that's how these things systematically work. The next one will, the x squared things will cancel, and the x cubed will be the next non-vanishing one. That's why you have to go all the way to third order. Good, so that's also pretty satisfying. That's starting to get us an idea where this 1 over r cubed business come from, where that beta over r cubed came from, and the nature of it, because this is not a 1 over x cubed that holds true arbitrarily close, right? It's a good approximation when you're far away from your object. Okay. We can do another version of this, since we got a minute or two. We can do another version of this. I'm going to draw a different picture. Because imagine if you wanted to get this approximation from any point in space, for now we just got it on the x-axis, so that can get complicated. But we're going to do another version of this, and then later we'll develop more general formalism, but this is pretty good. So again, minus L over two to L over two. But this time, we want the potential at a point on the y-axis. And again, we're just gonna add up a bunch of little dm's. But the distance from this dm to here, again, this is, x prime. And so now, again, we're gonna have v of y equals minus g integral dm over y minus x prime. dm prime. That does the trick. That does the trick. Always remember what we're looking at is u is equal to minus g m over r, and v is equal to minus g m over r, right? So what we're doing is we're just integrating at each mass point. We got to get the distance to there. So actually, this may not be such a good way to write it. Unless we put this as a vector magnitude, we call this a vector just to indicate. We need that hypotenuse, right? Hypotenuse. So this will work. We've got minus g. We've got integral lambda dx prime. And what's the distance along my little dotted line here? Okay, that's the square root of x prime squared plus y squared. Y squared plus x prime squared. That's more like it, right? This was just indicating the distance between these two points. And we do one more step. Here we go. I'll go ahead and erase these. So once again, v y equals minus g. Now that lambda again is just total mass over the length. And then we've got minus L over 2 to L over 2 dx prime root y squared plus x prime squared. You can drop the prime at this point. No, we're integrating over, right? So now this is going to be, what is this, some inverse hyperbolic something or other. Okay, you guys could look this up if you want to do the exact integral, but this would be one where it would be interesting to expand the integrand and then integrate. So I'll probably assign this one too. What we're looking for, by the way, so.
Yeah, you could use inverse sine. I need to use substitution.
Yeah. Prime squared. No, that would be a minus. Those inverse sine and cosine would have a minus sign there.
That's why I'm thinking you need to use substitution.
Yeah, it could be
Put
hyperbolic.
it in the right form.
But what we want to find is that limiting business, right? So what's the limiting form of this thing for y very large? So we seek y much, much greater than L behavior, we'll call it that. And we can do it by getting the exact integral and then doing some expansion, or by expanding the integrand. But in either case, we're going to find v of y is going to go as minus gm over y and I'm gonna use a different letter plus some b over y cubed. That's gonna be generic. Yeah. We got a minute or two, we'll just think about this a bit more. This one is gonna really just fall in your lap, okay? And this one's a little more challenging. And then you're gonna see, well, that's a fair amount of work and we're only getting that, but what if we just had an arbitrarily shaped object and we're anywhere in space, okay? Then we need some, we need some more systematic method, which is what we're gonna develop. But this is a perfect way to approach it because we know our Taylor expansions. We make good use of them. So this problem here again was the potential when viewed from the x-axis, and here we're gonna get the potential when viewed from the y-axis. So how could we expand this? Let's have a look. Okay, if I erase this one, you guys have this going on, right? So that integral is what's interesting now. So we have integral minus L over 2, dx prime root y squared plus x prime squared. Now we're looking for y very large. And since y is not part of the integration, we could do this. We could even have 1 over y, or magnitude for whatever it's worth, integral dx prime root 1 plus x prime over y squared. Now, for x prime over y small, we could expand this thing, okay, in a Taylor expansion. So, expand, we'll write it this way, 1 plus x prime over y primes squared to the 1/2 in the Taylor series, or just say expanded. And x prime over y is your small quantity again. So you could say I've got f of z equals 1. Oh, by the way, there's a minus 1/2, very key. So we have 1 plus z to the minus 1/2. And we expand it to a couple of orders. And remember, the z is that quantity squared, but that's okay. So f prime of z is equal to negative 1/2, 1 plus z to the negative 3/2. You probably only have to expand it that far. We're going to have to do the f double prime. So what's our Taylor expansion? F of z, when z is equal to 0, right? We're expanding around z equals 0, obviously, small quantity, okay? So when z equals 0, we have a 1. And when z equals our, so we have a 1 here, and then f prime of 0, we have minus 1/2. This is a linear term. Z. I think that's as far as I'm going to take it. What do you guys think? So the idea is to take this and and substitute it, I'm gonna put it in here anyway, we can't restrict, so now we have, integral minus L over two, L over two. We've got dx prime, and now, I'll put the one over y out here. But dx prime is right here. And what are we integrating? One minus 1/2 x prime squared over y squared. I've done too much for you guys, but nothing like that. So if we go back to here, we've got the minus GM over capital, GM over L in front of this, right? And then we've got this thing, which I've kind of broken down. And you do that to that many steps, and in fact, you already see, you're gonna get an L here, you're gonna get 1 over y, there's that behavior right there already, okay? And, yeah, you can integrate something up, and you're gonna get the 1 over y cubed behavior by multiplying that out. Okay. So I'm gonna add this to the homework. Definitely. So right here, homework. And this is exactly our goal. We'll get this thing here and we'll know what that letter B is. Okay. And we can compare it to the first one, and you're going to see there's a different sign between the A and B. A different sign depending on whether you're approaching from this side or approaching it from that side. Okay, good. That's a good spot to have